Hi guys, Mr. Arnold. Let's talk a little bit about water resources because this is a pretty important topic. Of all the things that we talk about all year, really, there are a lot of things that are pretty important. When we talk about mineral resources and electricity and power and all those things, those are important, but you can't live without water. So that makes it even more vital. What this little representation here is that this little ball on the top here, this is all of the Earth's water. Now, you may think, well, doesn't water cover all of the Earth? And it does, but remember, it only covers it to a certain depth. So while 70% of the Earth's surface is covered with water, volume-wise, it basically makes up a sphere this big. Now that is pretty big. That's an enormous volume because remember, it's going up, okay, as well as going out. So that's a lot of water. What is somewhat problematic for us, though, is that only about 3% or so of that is actually freshwater. Now, freshwater obviously is what we're going to need most of the time. And then of that fresh water, only of that 3%, only about 0.5%, only about 0.5% of that is actually readily available to us in the form of lakes, rivers, and streams and stuff like that. So here's the overall breakdown. So about 97% of the Earth, the water that we have on Earth is in the oceans or is salt water in a sea or something. So of that 2.78% that's fresh water, about 77% of that is tied up in ice and glaciers. Now that's still important to us. And as those melt, what becomes really bad is if they melt and go into the ocean, then that becomes salt water. And it has a myriad of effects. It affects climate and the thermohaline circulation and all that stuff that we talked about. But perhaps most importantly too, as far as water is that we no longer have that freshwater reserve there. About 22% of it is below ground in aquifers and stuff like that. And obviously we're going to talk about us pulling some stuff out of there, and we already have in our discussions of the Ogallala Aquifer. About 0.47% lakes, rivers, streams, and then about 0.03% of that is atmospheric water. So that groundwater, those aquifers, essentially this is a little diagram of what an aquifer is. An aquifer is just some sort of usable groundwater. Now, what is important to realize is that an aquifer isn't necessarily like an open space in the ground. It's not like the underground sea or anything like that. An aquifer basically is that there's small spaces within rocks and sediment, and that water gets stored there. And so we can pull that water out by basically putting a well down there, and we can pull that out. It's not, in general, it's not like there's just a big pool of water. Now, sometimes there is, but that's not always the case. And so within that, we've got a couple of different definition type terms that we need to know here. So the water table right here, this line, this little dashed line, that is the water table. And the water table, what it represents is that's the top level where water starts to seep through the soil. So if you were like digging a hole, then water would start to fill up at that point. That's where the water table is. And where that is varies pretty greatly. So in some places in Tennessee, it might not be right near the surface. I know I grew up in Florida, and you couldn't dig very far underground, or the water was pretty much right there because the water table was only a couple of feet underground in a lot of places. So that's why I say nobody in Florida is going to have a basement. And then what you've got there, the water table basically marks the top of what we call an unconfined aquifer. So that's the top layer of water that basically isn't trapped in. Now, the good news there is the unconfined aquifer, relatively easy to recharge because basically water is going to fall on the soil, it's going to trickle down, and eventually it's going to fill up that unconfined aquifer. Now, it can be depleted if we're pulling it out quickly. And then we've got confined aquifers below that. And let me see if I've got a better diagram here. Yeah, or at least a little bigger. The confined aquifers here are trapped between two impermeable layers. Now, remember, permeable means that water is able to get through it, and impermeable means that water can't get through it, or at least that it would take hundreds or thousands of years for the water to penetrate through that rock. So it's hard bedrock and stuff isn't able to easily penetrate it. So that's a confined aquifer. Now that's where we, in many places, have enormous supplies of water, like the Ogallala Aquifer is a good example of that. And it's trapped between two impermeable layers, and so it's a permeable layer of rock. There's a lot of water stored in there. But again, it's not just an open area underground, it's in rock. And so this goes to when we talked in the Ogallala stuff about why don't we just pump water back in, easier said than done because it's not just an open space. You can put water back in, but it's not as easy as if you were just, say, filling up a pool or something like that. A couple other definition terms. And so again, this is unconfined and confined areas. I don't know why I have multiple slides of all that. I've got several slides of all that. Right here, what's really important for us is if we look right here, this is the recharge area. So as water falls, then this is the permeable area right here. And so the water can go through here and it comes down and it can recharge. Now this layer right here, layer 2 in both cases, those are impermeable. Okay, and so this is going to be a confined aquifer in here. Now it's unconfined over here because we can recharge it this way. And this is, again, going back to our Ogallala aquifer, the unconfined region of the Ogallala aquifer is up towards South Dakota and stuff. And so when they get precipitation there, it can refill the aquifer from there. But as you go through, as you go south throughout the Midwest there in that aquifer's region, it can't get recharged very quickly because it can't penetrate through this impermeable soil here. Impermeable rock, not soil. Okay, last thing we want to talk about for this particular stuff is the idea of saltwater intrusion. Okay, and so we're talking about like if you're at the coast, okay, if you've got a house relatively near the coast, or really if you're pretty much anywhere in Florida, you've got saltwater intruding through permeable levels of rock. And so you've got some fresh water here, but you also have salt water that's penetrating in. And what happens is, let's say that you've got a house here on the coast and you drill a well to go down into the fresh water. Okay, so you're pulling water up through this well that you have here. Now what happens, as you might imagine, is that starts to, over the course of time, and if many people are doing it, it starts to drain the fresh water. And what actually happens is that the freshwater level is going to change, and so all of this area in here then starts to get invaded by the saltwater, and that's what we call saltwater intrusion. This is what's called a grab the pen, sorry. This is what's called a cone of depression. And what's being depressed basically is the level of the fresh water. So that's going to allow the salt water to come in. The reason it's called a cone is because it's going to form kind of a conical shape here as it pulls it out. Because remember, it's not just a straight line. We're talking about three-dimensional area, so it's pulling out a cone. Okay, and so that's the idea behind saltwater intrusion. Okay, so hopefully that gives you an idea of the water resources that we have available to us. And remember that, of course, this is just definition stuff. You got to do the activities in class to know what's going on every